Hey everyone, welcome into this first lecture video on indeterminate forms and L'Hopital's rule. The first video that we'd like to make is about Cauchy's mean value theorem. So we're going to state the theorem and then we're going to prove it, and I hope that this proof looks familiar because Cauchy's mean value theorem is really just a generalization of the standard mean value theorem for derivatives from Calculus 1. So let's start by stating the theorem. The theorem says, suppose that we have two functions, f and g, and suppose these two functions are continuous on a closed interval and differentiable on an open interval. So suppose f and g are functions continuous on a closed interval from a to b and differentiable on the open interval from a to b, same interval, but remember derivatives can have problems at endpoints, right? So we have to say that this is differentiable on the open interval, and then we're going to make one more assumption here, one more hypothesis for our theorem, and that is that g prime of x, so the derivative of g, is not 0 for any x in this open interval. So maybe this is a little loose way I've said it, but the derivative is not 0 at all for all x, basically, right? It's never 0. The derivative is never 0 inside this interval. And the conclusion is then there exists a number c strictly between a and b. So number c in the open interval, we'll say it this way, but this means that it's strictly between a and b, right? Such that, and again, this sounds a lot like the mean value theorem statement, but now here's the conclusion of the Cauchy mean value theorem. So this one says then at this point c, the ratio of f prime of c over g prime of c, so the ratios of the slopes of the tangent lines at this point, is equal to the ratios of the average slopes. So f of b minus f of a, or the average rates of change, over g of b minus g of a. All right, and if you think of these as slopes, then they would both be divided by b minus a, right? And those would cancel. So you end up with this ratio right here. So this is the statement of Cauchy's mean value theorem. And what we want to do now is prove this. We're going to use this to prove some other facts about calculus that I think you might have even heard before, but probably not proved. But yeah, we want to prove this. So the proof of this theorem is very similar to the proof of the actual mean value theorem. Before we do the proof, let's notice one thing. So notice, if you put g, this function g of x, just equal to x, all right, then what happens? Well, then g prime of x is constant. It's equal to 1, all right? G of b is equal to b, and g of a is equal to a, of course, right? That's what it means. It's an identity function. And when you do that, since the derivative is always 1, then it's not 0, right? When you do that, you then plug back into this formula. Look what you get. So then the Cauchy MVT says, you know, given all of the same assumptions on f, says that there exists a point c in this interval from a to b. This backwards e means there exists a point c such that, look what happens. F prime of c over g prime of c. Well, that's 1. So the left-hand side just becomes f prime of c. The right-hand side becomes, okay, f of b minus f of a. And then g of b minus g of a, well, we just said g of b is b, g of a is a, so this becomes b minus a. And that's exactly the usual mean value theorem, right? So Cauchy's mean value theorem is truly a generalization of the standard mean value theorem in the sense that it just replaces this identity function g of x with any function, right? But obviously, the Cauchy's mean value theorem should still apply when you specialize to this function g equaling just x, g of x equals x. And we already know that this is true, right? We've proved it. But let's remember how we proved this, because we're not going to prove Cauchy's version pretty much the same way. So here's our proof, or at least a sketch of the proof. Here's what we're going to do. Define a new function. So again, if you haven't proved the mean value theorem in a while, pause the video, go take a minute to think about how you would prove the usual mean value theorem, and then start back up at around this point, and you're going to find out that this is very similar, right? So here's the function that we're going to define. This function I'm going to call h of x. H of x I'm going to define to be f of x minus f of a minus the ratio f of b minus f of a over g of b minus g of a times g of x minus g of a. All right? Now, in the actual mean value theorem, what's different, right? How is this different from the proof of the actual mean value theorem? Well, these two terms, in the actual mean value theorem, we just used the identity function from up here, right? We didn't know that we were doing that, but that's exactly what we did, because the function that we defined to prove the mean value theorem has b minus a and then x minus a up here, right? So that's the difference. Now what we have to do is we have to check that this function, so I'm going to claim this, that h satisfies the hypotheses of Rolle's theorem. And again, this is the same way that we prove the MVT. So for h to satisfy the hypotheses of Rolle's theorem, then h should be continuous on the closed interval. Well, is it? Remember, we're building this function out of f and g, and the f and g satisfy the properties that we set out, that we assumed in the theorem, right? So f and g are both continuous on a, b. And then we get to assume that f and g are both differentiable on a, b as well. So, on the open interval a, b, and the g prime is not 0, right? So we look at this, and we see, yeah, this is built out of continuous functions. We didn't do anything crazy, right? So yes, this function is continuous. So there's criteria number 1 for Rolle's theorem. Criteria number 2 is that h should be differentiable. And again, because we built this h out of two functions that are differentiable on the interval a, b, and both of the functions themselves, right, these ratios are all numbers, and these f of a, this ratio, this number, these are all numbers. F and g just show up as, linear multiples of themselves. And since those are assumed to be differentiable on AB to start with, then yeah, of course, this is differentiable on AB. All right, and then number 3, we need to check. So this is different, right, for Rolle's theorem as opposed to the mean value theorem. Rolle's theorem now says what? It has to obey that h of a should equal h of b. So this is the question mark. So this is the one we have to check now. And so let's plug in. H of a, just plug in, remember, everything's a constant except for x in this formula, right? So this is f of a minus f of a minus f of b minus f of a over this g of b minus g of a times g of a minus g of a. And look what happens, right? So what are we going to have? When we plug in a, we get these cancel, doesn't matter what this is. This is 0. All right. Now we need to check h of b, right? So h of b is next. And by the way, whatever we get here, it doesn't really matter, right? We just need to make sure that it's the same value that we get for h of b. So now it matters, right? Now we better get 0. We can't force it, though. We just have to plug in and see what happens. So when we plug in b, we have f of b minus f of a minus this ratio. That's all going to be subtracted, right? And then g of b minus g of a. And then over here, this becomes g of b minus g of a. And look at this. We've got these two terms cancel. And then we've got something, f of b minus f of a minus itself, right? F of b minus f of a minus f of b minus f of a. So that whole thing is also 0. So since these are equal and the function obeys the continuous and differentiable hypotheses, so then we can say, so this is check mark now, so thus Rolle's theorem applies, right? And that's good because now we're going to use Rolle's theorem, and then we're basically done. All right. Therefore, what does Rolle's theorem tell us? So therefore, there exists a number C strictly between A and B such that I'll abbreviate h prime of C is equal to 0. That's the conclusion of Rolle's theorem. So on one hand, we've got 0. On the other hand, we have h prime of c, right? Well, we can compute the derivative because this function, if we scroll back up, this function is differentiable and we can compute it. The derivatives of these are just going to be f prime, 0, that's a constant, right? This constant is going to hang around. G prime, 0, that's a constant, right? So what we end up with is that we get f prime of c minus this ratio, f of b minus f of a, over g of b minus g of a, all times g prime of c, right? So that's just, again, taking the derivative, and everything's linear here. It's nice. I mean, the functions are here, but with respect to the functions, everything's linear. We take the derivatives, and the constants go away, and then plug in c for x after you take the derivative. Take the derivative first, then plug in c. But this whole thing, by Rolle's theorem, is got to equal 0, right? So at this point, we can just start rearranging. So what we can do is we can add this whole term to the other side, and we get that f prime of c is equal to our ratio times g prime of c. And at this point, we finally need that last assumption. So up to this point, we've only used, if we scroll back up to the statement of our Cauchy mean value theorem, we've only used the assumptions that f and g are continuous on the closed interval, differentiable on the open interval. We have not yet used this fact that g prime of x is not 0 for any point, right? But now we need to use it, because now, to get the result that they claim, right, that is claimed by the theorem, we need to divide through by g prime of c. And we're allowed to do that because that's not 0, right? So now we can say, finally, since g prime of c is not 0, we obtain the result. So, and the result is, right, that at this point c, there exists a point c. We don't know what the point c is, by the way. Not yet. I mean, you got to do more work if you want to find the point. The mean value theorem just gives you existence of the point. So it says the point exists. Yeah. So there, I was going to write something else, but we don't need to do it because that's the result that we wanted. We already got the existence of the point up here. It's just there exists a point. So there exists a number c. All right, and there's the result. So this is the Cauchy mean value theorem proved. So we've now proved it. That means we completely believe the Cauchy mean value theorem. We're going to use this in the next video to prove another result. And we might see this later on in the semester because this is a very important theorem. I mean, it's the mean value theorem generalized, right? So anytime you generalize something, there's at least a chance that it might be more useful in like a more diverse setting. So this is a good one to keep in mind, and we will see it again soon.